This video is a second part of a two-part demonstration on the functionality of the moment distribution method. The first part analyzed moment distribution in a two-span beam with fixed outside supports. The following part will analyze the moment distribution in a two-span beam with one fixed outside support and one pinned outside support. Once again, the first step in determining the moment distribution in a beam is to calculate each span's stiffness. Span AB is modeled as having a fixed support condition, which means its stiffness is given as 4EI over L, or in this case 12,667 Newton millimeters. Span BC, however, is modeled as having fixed pinned support conditions, which corresponds to a stiffness of 3EI over L, or 14,250 Newton millimeters. Once we have the stiffnesses, we calculate the distribution factors just as we did in the first part. By allowing rotation at support C, the distribution factors have adjusted. Distribution factor BA increased from 0.4 in part 1 to 0.47, and distribution factor BC decreased from 0.6 in part 1 to 0.53. Here's a summary of the distribution factors. Now we determine the carryover factors. Span AB displays the same behavior as before and will carry half of an applied moment at B over to support A. Span BC, however, no longer will carry a moment to support C. This is because support C cannot support a moment due to the pinned connection. We will use the same 2000 Newton millimeter moment applied at the center support for this part of the demonstration. But before we get started using the physical model, let's take a look at the theoretical calculations. Of the 2000 Newton millimeter applied moment, 940 Newton millimeters is taken by span AB and 1060 Newton millimeters is taken by span BC. Half of the 940 Newton millimeters in span AB will get distributed to support A. Now let's see if we can make this happen in the physical model. The first step for this loading scenario is as shown. The end supports are fixed and the moment is applied at the center support. Here you can see the LabVIEW interface for this step. The end supports are fixed and the moment has been applied. Now let's see this in action. Stephen has applied the moment and is unlocking the center support, allowing it to rotate freely. Here are the corresponding shear, moment, slope, and deflection graphs for this step. They should look familiar, as these are the same set of graphs from the initial loading of the previous example. Now we will unlock the right support, allowing it to rotate freely and releasing the moment there. You can now see the right support has been unlocked in the LabVIEW interface, shown by the indicator's dark green color, and a rotation has developed as evident in the dial beneath the support. Now let's take a look at the physical model. Watch the dial at the right support as the rotation is released. The moment at support C is now 0, and the moment at support A has increased slightly to account for the reduction in stiffness in span BC once support C is unlocked. Now we will lock the center support, then unlock the left support in preparation for applying a moment at the left support to determine the reaction there. The center support has been locked in the LabVIEW interface and support A has been unlocked. Note the rotation that has developed at support A. Watch the dials at supports A and B. B will remain motionless as it is locked, while A adjusts as it is unlocked. The moment diagram remains unchanged for span BC because of the isolation provided by locking support B, while the moment at A has been reduced to 0. Now we will finally get the information we have been searching for. In order to find the rotation at A, we will apply a moment at that support until the rotation reads 0. This will tell us how much of a moment was required to maintain the 0 rotation fixed support. The theoretical reaction moment was calculated to be 470 Newton millimeters. Here you can see we applied a simulated reaction moment of 500 Newton millimeters in the LabVIEW interface because of a limitation of physical materials. However, this load is only a 6% difference and will not greatly affect our results. You can see the rotation in the dial at support A is slightly off of 0, but it's still very close. The moment diagram is slightly off here, but would have been equal to 0 at A with a more accurate applied moment. Now we will unlock all the supports and see how close our results from the simulated reaction moment are to the real case we are analyzing. All the supports are now unlocked in the LabVIEW interface. As you can see, the rotation at support A is not quite 0 due to the slight inaccuracy of the applied simulated reaction moment, but let's take a look at the physical model. There is little to no change in any support rotations when the center support is released. This means our rounding error is not too bad. Here we have the final shear, moment, slope, and deflection graphs. But let's take a look at these and those corresponding to the true support conditions side by side. There is a slight difference in the graphs, but you can also see that they follow the same trend and are highly similar. Next time you join us for one of these demonstrations, we'll make sure to have exact weights. In any case, thank you for watching, and we hope you enjoyed it.